While chemical formulas give us useful information about the number of each type of atom that are in a compound, we also see that they don't give us anything about the way atoms are connected. Because organic compounds are composed of primarily carbon and hydrogen, there are lots of different ways for the carbon and hydrogen atoms to be connected. And so one thing we do in organic chemistry is write something called a condensed structure. So what we're starting with here, we have a skeletal structure that's kind of an enhanced skeletal structure because I've already added in the hydrogen atoms. And we're going to see how we can write this as a condensed structure that simplifies the way we write it, but also gives us information about the atom's connectivity more than what we see when we just have the chemical formula. Remember that where we have CH2, that's the same as having a carbon with two hydrogens attached. The same would be true for CH or CH3 with the appropriate number of hydrogens. Let's look at how we can write this to show something about the connectivity. And we're going to start on the left side of the molecule, and we see we're starting with something that says H3C. Now notice at the other end of the molecule we see CH3. These both mean the exact same thing, and you're going to see it drawn in different ways. Usually on the left end it will often show as H3C, although not always. Sometimes it will still show as CH3, and that means the exact same thing. A carbon with three hydrogens attached. So we're going to write this condensed structure by writing first our CH3 because that's what we see on the left side of the molecule. Next, we're going to go to the next carbon, and we see that we have a carbon with a hydrogen attached, but we also have attached to that a CH3 group. And because that CH3 group is not in the main chain of the compound, our main backbone of the structure, what we're going to do is to put that into parentheses as a reminder that it's not attached to the backbone, but it's not part of this backbone of the molecule represented by that green line. So we do parentheses CH3. We go on, we have CH2 is the next piece of the molecule, CH2, and CH3. This is what's known as a condensed structure. It gives us something about the connectivity of atoms without actually drawing out the structure. Let's look at an example where we start with just the skeletal structure. First, we're going to add our hydrogen atoms in to all of our carbons. We see that these three carbons all have one other bond, so they're each going to have three hydrogens. The next carbon, which we see here, already has four bonds to other carbon atoms, so we're not going to add any hydrogens there. We have two hydrogens on the next carbon, one hydrogen there because it already has three other bonds, two hydrogens going up, and three at the very top. Going back to our chain of our molecule, we have two hydrogens on the next two carbons, and then three hydrogens on the last one. Now we can go through and draw our condensed structure that would represent the same information that we see here in this skeletal structure. So we start with our first carbon and we get CH3. The next one is just carbon. There's no hydrogen because we don't have any hydrogen atoms attached to it. But then we see that we have two CH3 groups attached to it. Again, like before, those CH3 groups are not part of the backbone or the main chain of the molecule. They are off to the side, so we're going to have to use parentheses to represent them. And so what we see is we have CH3 group times 2. So we have two CH3 groups attached to that carbon atom. We continue to the right, so we have CH2, then we have CH, but now we have a different group attached to the side chain, so we do need parentheses because it's attached as a side group. But what we see is that it has two carbons in it, but it's two carbons connected together. So we're going to show this as CH2, CH3. Notice that this is different than having two carbon atoms attached as separate groups. Here we have one group with two carbon atoms. So we represent that differently in our condensed structure. Next, we'll have our CH2, CH2, and finally one last CH3. So we see here that our condensed structure represents this molecular structure. Let's look at an example where we have double and triple bonds between carbon atoms. As we did before, we're going to draw in our hydrogen atoms first, and to make it a little bit easier, because we're just annotating our skeletal structure, we're just going to use this as a shorthand for our hydrogen atoms. So I'm showing just little lines coming from the carbon atoms to represent the number of hydrogens. So we have 3 hydrogens on the first carbon. The next 2 carbons, we have 1 each because the double bond counts as 2 bonds, so that each of those carbons already has 3 bonds to carbon, and so it only needs 1 more bond to a hydrogen atom. Next we have 2 hydrogen bonds. The next 2 carbons actually have no hydrogens because each of those carbons already has 4 bonds. Then we have 2 hydrogens on the second to last carbon and 3 hydrogens on the last one. Now we can look at writing the condensed structure by reading our molecule from left to right and writing down what we see. So we start with a CH3, a CH, CH, CH2, C, C, CH2, and CH3. Notice that there's nothing in the condensed structure that explicitly shows the double or triple bond. However, we can figure out that there have to be double and triple bonds present because when we draw the structure back from the condensed structure, we'll see that there are not enough bonds to carbon, and the way we complete that 4 bonds to carbon will be to create double or triple bonds. Let's look at an example where we have some different atoms involved. Just like in the previous examples, we're going to draw in our hydrogen atoms for each carbon. Notice that the hydrogen that's attached to the oxygen already has to be shown even in a skeletal structure. We can only have implied hydrogens when we're looking at carbon atoms. Now we can go through and write our structure, starting with CH3, CH2, CH, but we also have an OH group, and it's off to the side of the molecule. It's not part of the long chain of the molecule, so we put the OH in parentheses. Then we have CH2, and then we have oxygen. Note that this oxygen is not placed in parentheses because it is part of the chain or the backbone of the molecule. Because it's part of the longer chain, it does not need to be in parentheses. The first oxygen of OH was off to the side of the molecule, so it did have to be in parentheses. Next we have CH2. Next we have CHF. And here, fluorine is off to the side of the backbone, but it does not need to be in parentheses for the same reason that hydrogens are not shown in parentheses. Halogens, or group 17 elements, will only form 1 bond, so they have no option except to be off to the side of the molecule, just like a hydrogen atom. As a result, we do not put our halogens, so fluorine, chlorine, bromine, and iodine, in parentheses in a condensed structure. As we can see from oxygen, it can be part of a side group or part of the chain. Therefore, we have to distinguish which type of oxygen atoms are included in the molecule. Next, we have CH2 and then CH3. Just like hydrogen, halogens only form 1 bond, so parentheses are not needed. Other groups that are off to the side of the main backbone of the molecule must include parentheses, including OH groups, other elements, or carbon and hydrogen groups. Another example, this molecule contains 2 OH groups. So we add our hydrogen atoms in. And this is always easier to do ahead of time before you start writing the condensed structure, so you're not switching back and forth between writing the structure and counting hydrogens. So we write our CH3, CHOH with the OH in parentheses because it's not part of the main backbone of the molecule. CH2, CH2, and our OH. This OH at the end presents a unique situation because OH groups can be considered off to the side, or they can be considered as part of that chain in the way that this OH is drawn because it's at the end of the molecule. As a result, you will sometimes see this condensed structure written as we see on the screen now, or written without this second OH in parentheses. Either one will be considered correct.